Langchain Fireworks Chat Models. Description: Explain in detail. Langchain Fireworks is a conversational AI model specifically designed for interactive, creative storytelling. It's trained on a massive dataset of text and code, allowing it to generate engaging narratives, poems, scripts, and even musical compositions. Inputs. Input 1. Explain in detail prompt. This is the user's input. Typically a text message describing the desired narrative or creative output. For example, a user might provide a prompt like write a short story about a cat who travels through time. Input 2. Explain in detail. Context optional. Users can provide additional context to guide the model. This could include specific characters, settings, themes, or even snippets of previous outputs to build upon. Outputs. Output 1. Explain in detail. Generated text. The model outputs a creative text format, like a story, poem, script, or musical score, based on the user's prompt and context. Output 2. Explain in detail. Metadata. The model may also output metadata about the generated content, such as its genre, style, and any specific techniques used. Steps. Step 1. Explain in detail. Prompt processing. The model first analyzes the user's prompt and any provided context to identify key elements like characters, plot points, and desired tone. Step 2. Explain in detail. Creative generation. Using its extensive knowledge base and creative capabilities, the model then generates text that aligns with the user's input. Metrics. Metric 1. Explain in detail. Human evaluation. The model's output is typically assessed by human evaluators who judge its quality, creativity, and coherence based on various subjective criteria. Metric 2. Explain in detail. Automatic evaluation. While more challenging, metrics like perplexity and blue scores can be used to evaluate the model's fluency and consistency with the provided prompt. Visualization plots. Visualization plot 1. Explain in detail. Word clouds. A visual representation of the frequency of words used in the generated output. Visualization plot 2. Explain in detail. Topic modeling. Visualization of the underlying themes and concepts captured in the text. Fine-tune parameters. Parameter 1. Explain in detail. Temperature controls the level of creativity and randomness in the output. Higher temperatures lead to more unexpected and diverse results. Parameter 2. Explain in detail. Top K. This parameter affects the model's selection of words during generation. Higher values allow for more diverse vocabulary. Uncertainty methods. Uncertainty method 1. Explain in detail. Confidence scores. The model can provide confidence scores for generated words or phrases, indicating its level of certainty in their appropriateness. Uncertainty method 2. Explain in detail. Multiple outputs to address uncertainty. The model might generate multiple outputs with varying levels of creativity and originality, allowing users to choose the one that best suits their needs. Challenges and fixes. Challenge 1. Explain in detail. Lack of contextual coherence. The model might produce text that is grammatically correct but lacks a clear narrative flow or logical connection between ideas. Sample use case that resulted in challenge 1. A user prompts the model to write a short story about a cat who travels through time, but the output jumps between different time periods without a clear explanation or reason for the transitions. Fixes to challenge 1. Contextual prompts. Users can provide more detailed context, outlining the story's structure or providing a timeline of events. Iterative feedback. The model can be prompted to refine the story by providing feedback on previous outputs, allowing it to improve coherence. Challenge 2. Explain in detail. Overly generic or repetitive output. The model may sometimes produce text that is generic, lacking unique elements or a distinct voice. Sample use case that resulted in challenge 2. A user prompts the model to write a poem about a lonely tree, but the output is a generic poem about a tree without any specific details or emotions. Fixes to challenge 2. Specific constraints. Users can provide specific requirements like a particular rhyme scheme, word choice, or emotional tone to guide the model towards more unique output. Seed values. By providing a seed value, users can influence the model's random generation process, leading to more diverse and original outputs. Langchain Fireworks Chat Models. Chat Fireworks. Description. Chat Fireworks is a large language model (LLM) built on top of Langchain, specifically designed for interactive and conversational applications. It leverages the power of Langchain's capabilities, including chain composition, memory management, and external tool integration, to enhance its conversational abilities. Inputs. Prompt the user's input or question. It can be a natural language query, a structured command, or a combination of both. Context. This includes any relevant information from previous interactions, external knowledge sources, or user-defined data that helps the model understand the conversation's history and provide more accurate and coherent responses. Outputs. Response. The LLM's generated text response to the user's prompt. It can include summaries, explanations, creative content, code snippets, and more, depending on the context and prompt. Metadata. This can contain additional information about the response, such as confidence scores, sources of information used, or timestamps. Steps. Input processing. The prompt is first pre-processed and tokenized. Context retrieval. Relevant information from memory and external knowledge sources is retrieved based on the prompt's context. Chain execution. The prompt is passed through Langchain chains, which can include a sequence of components like retrieval, summarization, translation, or code generation. Response generation. The final response is generated by the LLM based on the outputs of the chain execution and the retrieved context. Response. Post-processing. The response is further processed, for example, by adding metadata or formatting it for better readability. Metrics. Response quality evaluates the relevance, accuracy, and coherence of the generated response based on human feedback or objective criteria. Conversational fluency assesses the naturalness and smoothness of the conversation flow, taking into account factors like coherence, turn-taking, and topic switching. User satisfaction measures user engagement and overall satisfaction with the chatbot experience. Visualization plots. Response length distribution visualizes the distribution of response lengths over time, which can help understand the model's verbosity and its adaptability to different prompt types. Context usage patterns analyzes how frequently and effectively the model uses contextual information from previous interactions and external sources. Chain execution times tracks the time spent on different stages of the chain execution, helping identify potential bottlenecks and areas for optimization. Fine-tune parameters. Learning rate controls the step size during the model's training process. Batch size determines the number of samples used in each training iteration. Epoch specifies the number of passes through the training data during the training process. Uncertainty methods. Confidence scores provides a measure of the model's confidence in its predictions, allowing users to assess the reliability of the response. Temperature scaling allows for controlling the randomness and creativity of the model's output, with higher temperatures leading to more diverse responses. Challenges and fixes. Challenge 1. Factual inaccuracy. Sample use case that resulted in challenge 1 when asked a question about a specific event. The model may provide incorrect details or invent information. Fixes to challenge 1. Enhance the model's training data to include more factual and accurate information. Integrate external fact-checking tools or knowledge bases into the chain to verify the models. Responses. Challenge 2. Lack of contextual understanding. Sample use case that resulted in challenge 2. The model may struggle to maintain context across multiple turns, leading to responses that are irrelevant or contradictory to previous interactions. Fixes to challenge 2. Implement memory mechanisms in the chain to store and retrieve relevant information from previous conversations. Utilize techniques like prompt engineering to provide explicit context cues to the model. Challenge 3. Bias and ethical considerations. Sample use case that resulted in challenge 3. The model may exhibit biases or generate responses that are offensive, harmful, or discriminatory. Fixes to challenge 3. Train the model on diverse and representative data to mitigate bias. Implement safety mechanisms to filter out potentially harmful or offensive content. Encourage user feedback to identify and address potential biases. Langchain Fireworks Embeddings. Description: the Fireworks Embeddings model is a large language model (LLM) designed for generating embeddings, numerical representations of text data. These embeddings capture the semantic meaning of text, allowing for tasks like similarity search, clustering, and classification. Inputs. Text: the input text that needs to be embedded. This can be a single sentence, paragraph, document, or even a collection of documents. Outputs. Embeddings: a numerical vector representing the semantic meaning of the input text. The dimension of the vector depends on the specific Fireworks model used. Steps. Text preprocessing: the input text is preprocessed, including tasks like tokenization, normalization, and removing stop words. Embedding generation: the preprocessed text is then fed into the Fireworks model, which generates the embedding vector. Metrics. Cosine similarity: this metric measures the similarity between two embedding vectors, ranging from 0 completely dissimilar to 1 identical. Visualization plots. T-SNE distributed stochastic neighbor embedding: this technique allows for visualization of high-dimensional embedding vectors in a 2D or 3D space, facilitating visual exploration of text similarities and relationships. Fine-tune parameters. Learning rate controls the step size during the model training process. Batch size determines the number of data points used in each training iteration. Uncertainty methods. Dropout: a technique that randomly drops out neurons during training to improve model robustness and reduce overfitting. Challenges and fixes. Challenge 1: handling out of vocabulary OOV words. Words not present in the model's vocabulary might not be properly embedded. Sample use case that resulted in challenge 1: a user might input a technical term or a newly coined word that the model has not encountered before. Fixes to challenge 1: employ techniques like subword tokenization, where words are broken down into smaller unit subwords that are more likely to be in the vocabulary. Challenge 2: maintaining consistency across different models using different Fireworks models or versions might result in variations in embeddings for the same text. Sample use case that resulted in challenge 2: a user might switch between different Fireworks models for their project, potentially leading to inconsistent results. Fixes to challenge 2: use a specific version or model consistently for all tasks, or implement techniques like embedding normalization to reduce variation. Langchain fireworks embeddings. Fireworks embeddings. Description. Fireworks embeddings is an embedding model that utilizes the powerful fireworks algorithm to generate high-quality embeddings for text data. It excels in capturing the semantic meaning of text, facilitating applications such as text similarity search, clustering, and classification. Fireworks embeddings leverages an ensemble of pre-trained language models (PLMs) and a novel clustering algorithm to achieve its superior performance. Inputs. Text. The input text data for which you want to generate embeddings. This can be a single string or a list of strings. Outputs. Embeddings. A list of numerical vectors representing the semantic meaning of the input text. Each element in the list corresponds to a single input text. Steps. Text preprocessing. The input text undergoes preprocessing steps such as tokenization and normalization to prepare it for embedding generation. Embedding generation. Fireworks embeddings utilizes a diverse ensemble of pre-trained language models (PLMs) to generate embeddings for the input text. The models may include popular options like BERT, Roberta, and XLNet. Clustering. The embeddings from different PLMs are then clustered using a specialized clustering algorithm. This algorithm groups similar embeddings together, effectively capturing the semantic relationships between different parts of the input text. Final embedding. The final embedding for each input text is derived from the cluster center, associated with its embeddings from the different PLMs. This step ensures that the final embedding represents a comprehensive understanding of the text's semantic meaning. Metrics. Cosine similarity. This metric measures the similarity between two text embeddings based on their cosine angle. It is commonly used to evaluate the performance of embedding models in tasks like text similarity search. Jensen-Shannon divergence. This metric assesses the dissimilarity between two text distributions, capturing the difference in semantic meaning between two pieces of text. Visualization plots. T-SNE plot. This visualization method reduces the dimensionality of the embedding space, allowing for the visual representation of text data in 2 or 3 dimensions. It helps in identifying clusters of similar text and understanding their relationships. UMAP plot. Similar to T-SNE, UMAP uniform manifold approximation and projection is another dimensionality reduction technique used to visualize high-dimensional embedding spaces. It often provides a clearer and more informative visual representation compared to T-SNE. Fine-tune parameters. Number of PLMs. The number of pre-trained language models used in the ensemble can be adjusted to balance performance and computational resources. Using a larger ensemble generally results in better performance but requires more time and resources. Clustering algorithm. Fireworks embeddings offers various clustering algorithms to choose from, such as k-means, DBSCAN, and hierarchical clustering. The choice depends on the specific application and desired characteristics of the clusters. Uncertainty methods. Ensemble variance. Fireworks embeddings can estimate the uncertainty of the generated embeddings by analyzing the variance across the embeddings from different PLMs. Higher variance indicates greater uncertainty. Confidence score. By analyzing the clustering process, Fireworks embeddings can provide a confidence score for each generated embedding. This score reflects the confidence level in the model's ability to accurately capture the semantic meaning of the text. Challenges and fixes. Challenge 1. High computational cost for large datasets. Fireworks embeddings may require significant computational resources for generating embeddings for large datasets due to the ensemble approach and clustering algorithms. Sample use case that resulted in challenge 1 when processing a massive dataset of product reviews. For semantic similarity analysis, the computational cost of fireworks embeddings became a bottleneck. Fixes to challenge 1. Consider using a smaller ensemble of PLMs for efficiency gains. Utilize distributed computing or cloud resources to parallelize the embedding generation process. Explore techniques like early stopping or dimensionality reduction to optimize the clustering phase. Challenge 2. Sensitivity to hyperparameter tuning. The performance of fireworks embeddings can be influenced by the choice of hyperparameters, such as the number of clusters and the clustering algorithm. Sample use case that resulted in challenge 2 when applying fireworks embeddings for document clustering. The choice of the number of clusters had a significant impact on the resulting cluster quality. Fixes to challenge 2. Conduct thorough hyperparameter tuning using cross-validation techniques to identify optimal settings for the specific application. Explore automated hyperparameter optimization tools to streamline the process and discover robust configurations. Consider using techniques like silhouette analysis or elbow method to evaluate the quality of clusters and guide hyperparameter selection. Langchain Fireworks LLMS. Description. Explain in detail. Langchain Fireworks is an experimental LLM designed for creative writing and brainstorming. It utilizes a unique approach that combines multiple language models, each specializing in a different aspect of creativity, to generate text that is more engaging, imaginative, and surprising than traditional LLMs. Inputs. Input 1. Explain in detail a prompt or a starting point for the creative text generation. This could be a simple idea, a few keywords, or even an existing piece of text that the LLM can build upon. Input 2. Explain in detail optional parameters to guide the creative process. These parameters can include things like desired length, tone, or specific elements to be included in the output. Outputs. Output 1. Explain in detail a creative text piece generated by the LLM, potentially incorporating elements of different genres, styles, and perspectives. Output 2. Explain in detail optional output data, such as a summary of the creative process, insights into the model's choices, or potential alternative creative paths. Steps. Step 1. Explain in detail. The initial prompt is analyzed and broken down into its constituent parts. Each part is then assigned to a specialized LLM that is best suited to handle it. Step 2. Explain in detail. The specialized LLMs generate text based on their respective inputs, creating different creative elements that are then combined into a cohesive whole. Metrics. Metric 1. Explain in detail novelty. How original and unexpected is the generated text? Metric 2. Explain in detail relevance. How well does the text relate to the original prompt and the specified parameters? Visualization plots. Visualization plot 1. Explain in detail a visualization of the creative process, showing how different LLMs contributed to the final text. Visualization plot 2. Explain in detail a map of the creative landscape, showing potential alternative creative paths and their associated strengths and weaknesses. Fine-tune parameters. Parameter 1. Explain in detail LLM weights. The relative importance of different LLMs in the creative process. This can be adjusted to influence the style and tone of the output. Parameter 2. Explain in detail creative constraints, rules and boundaries that the LLMs must adhere to during the creative process. This can be used to ensure the text stays within a specific genre, length, or thematic scope. Uncertainty methods. Uncertainty Method 1. Explain in detail confidence scores. Each LLM provides a confidence score for its generated text, indicating how certain it is of its output. This can help identify potential issues and guide the creative process. Uncertainty Method 2. Explain in detail entropy, a measure of the randomness and unpredictability of the generated text. This can be used to assess the creativity and originality of the output. Challenges and fixes. Challenge 1. Explain in detail incoherence. The output text may not make sense or have a coherent narrative due to the combination of different LLMs with different styles and perspectives. Sample use case that resulted in Challenge 1. A prompt about a dystopian future might result in a text that jumps between different storylines and perspectives, lacking a clear plot or message. Fixes to Challenge 1. Post-processing techniques can be used to smooth out the narrative and ensure coherence. These techniques might involve identifying and removing conflicting or redundant elements, linking storylines together, or adding transitional sentences to improve flow. Challenge 2. Explain in detail bias and stereotypes. The output text may contain biases or stereotypes that reflect the biases of the individual LLMs used in the process. Sample use case that resulted in Challenge 2. A prompt about a fictional character might result in a text that reinforces traditional gender roles or perpetuates negative stereotypes about specific groups. Fixes to Challenge 2. It is important to carefully select LLMs that are known to be relatively unbiased and to implement safeguards against potential biases. This may involve using human oversight, filtering output for problematic language, or incorporating fairness metrics into the model evaluation process. Langchain Fireworks LLMS Fireworks. Description. Explain in detail. Fireworks is a framework for building large language model applications that is designed to be easy to use and extend. It provides a set of building blocks for creating applications that use large language models for tasks such as text generation, question answering, and summarization. Inputs. Input 1. Explain in detail. Fireworks applications can take a variety of inputs, including text, images, and audio. The specific inputs required will depend on the specific application. Input 2. Explain in detail. Fireworks applications can also take a variety of parameters, such as the temperature of the model, the number of tokens to generate, and the top K sampling method. Outputs. Output 1. Explain in detail. Fireworks applications typically produce text outputs, but can also produce other outputs such as images or audio. Output 2. Explain in detail. The specific outputs produced will depend on the specific application. Steps. Step 1. Explain in detail. Fireworks applications typically involve a series of steps, such as tokenizing the input, encoding it into a numerical representation, feeding it to the model, and decoding the output. Step 2. Explain in detail. These steps can be customized to achieve different results. Metrics. Metric 1. Explain in detail. Fireworks applications can be evaluated using a variety of metrics, such as perplexity, blue score, and rouge score. These metrics measure the quality of the generated text. Metric 2. Explain in detail. The specific metrics used will depend on the specific application. Visualization plots. Visualization plot 1. Explain in detail. Fireworks applications can be visualized using a variety of plots, such as attention maps and probability distributions. These plots can help to understand the model's reasoning process. Visualization plot 2. Explain in detail. The specific plots used will depend on the specific application. Fine-tune parameters. Parameter 1. Explain in detail. Fireworks applications can be fine-tuned to achieve better Performance on specific tasks. This involves adjusting the model's parameters to optimize its performance on a particular dataset. Parameter 2. Explain in detail the specific parameters that are fine-tuned will depend on pay. Specific application. Uncertainty methods. Uncertainty method 1. Explain in detail. Fireworks applications can use a variety of uncertainty methods to estimate the confidence of the model's predictions. This information can be used to identify areas where the model is uncertain or to provide more nuanced responses. Uncertainty method 2. Explain in detail. The specific uncertainty methods used will depend on pay. Specific application. Challenges and fixes. Challenge 1. Explain in detail. One challenge is ensuring that the model generates coherent and grammatically correct text. Sample use case that resulted in challenge 1. A user might provide a prompt that is incomplete or ambiguous, leading to the model generating text that is not grammatically correct or does not make sense. Fixes to challenge 1. This challenge can be addressed by providing the model with more context or by fine-tuning the model on a dataset of grammatically correct text. Challenge 2. Explain in detail. Another challenge is preventing the model from generating biased or offensive text. Sample use case that resulted in challenge 2. If the model is trained on a dataset that contains biased or offensive content, it may generate similar content. Fixes to challenge 2. This challenge can be addressed by carefully curating the training data to remove biased or offensive content. It may also be helpful to use techniques such as adversarial training to mitigate bias.